When a person looks up and sees stars, they think they are seeing the present of the sky. But the sky does not show a present, it shows an archive. Light takes time to travel, and that delay turns the universe into a memory machine. The moon is seen with a delay of just over a second, the sun with a delay of a few minutes, the center of the Milky Way with tens of thousands of years. Andromeda appears as it was millions of years ago. From there, each increase in distance is a deeper leap into the past. That is why the James Webb Space Telescope did not change astronomy by seeing farther in the everyday sense. It changed it because it stretched the reach of the observable past. Its real function is this: to push the limit of what can still reach us as information, and do so with a precision that was previously impossible. In a universe where everything is separated by enormous distances, the only way to study the beginnings is to catch ancient light. Light that was emitted when the cosmos was young and has since traveled through a space that did not stay still. Here comes the first concept that makes the scale of the universe strange. Space expands. It is not that galaxies fly through an empty room, it is that the room itself stretches, and when space stretches, it also stretches the light that passes through it. That light loses energy and changes color toward longer wavelengths, redshift. In other words, light that was born in ultraviolet or visible wavelengths, after billions of years of expansion, reaches us converted into infrared. That detail is not incidental, it is the key. If the early universe moved into infrared, a telescope designed for infrared is not a technological whim. It is a physical requirement to listen to an era that would otherwise remain silent. For decades, Hubble changed our view of the cosmos with images that seemed impossible. Tiny fields of the sky filled with galaxies. But Hubble works mostly invisible and some near infrared, and it has thermal and sensitivity limits. Webb was designed to go where visible light stops being useful, and where even infrared demands brutal discipline, cold, stability, and thermal darkness. Its main science depends on extremely weak infrared signals that, in practical terms, resemble more heat than light, as understood by the human eye. To detect them, the telescope cannot be a source of heat contaminating itself. If the instrument itself emits too much infrared, it blinds itself. It would be like trying to hear a whisper next to a running engine. That is why Webb has a giant layered sun shield, designed to separate the observatory from solar radiation and keep one side cold and stable. Its orbit is also part of the trick. It operates near the Lagrange point L2 of the Sun-Earth system, a region of space where the telescope can maintain a favorable geometry so that the Sun, Earth and Moon remain on the same side of the sun shield. It is not farther to see better. It is farther to be colder, more stable, and less contaminated. The scale of the universe is revealed when noise is reduced, not just when magnification is increased. That design is not meant to bring objects closer like binoculars. It is meant to capture photons arriving drop by drop from the deep universe. In the early cosmos, there is also a second problem: dust. Galaxies form stars. Stars are born in regions with gas and dust absorbs and scatters much visible light. But infrared passes through these clouds better. Thus, Webb not only delves into the past due to redshift, it also penetrates opaque environments that hid essential galactic formation processes. Up to this point, the idea seems simple: a more sensitive telescope in infrared that looks deeper, But the conceptual punch of scale appears when one understands what deep really means. In cosmology, distance is not a single thing. There is the distance one imagines as kilometers in a straight line. And there is cosmological distance, which depends on how the universe expanded during the light's journey. An object may have emitted its light when it was much closer than its current distance due to subsequent expansion. That is why, when we talk about seeing galaxies 13 billion years old, we are not describing a fixed space, but a story. The story of space growing while the message traveled. Webb is not just a camera, it is a history reader on a medium that stretches as you read it. Each deep photograph is not a postcard of the universe at a single moment. It is a superposition of epochs. In the same field of view, coexist relatively nearby galaxies and galaxies so remote that their light was emitted when the cosmos had only a tiny fraction of its current age. And even so, that past is not uniform. There are stages. There is a before and after the first stars ignited, a before and after the primordial gas was ionized, a before and after the universe was filled with heavy elements forged in stellar furnaces. In cosmology, the key word is not mystery, but timeline. The universe has an age measured with considerable precision, about 13.8 billion years. But the James Webb is looking at extremely early epochs when the cosmos was only a tiny fraction of that age. In those first hundreds of millions of years, the expected scene was dominated by small structures, dwarf galaxies with few stars, little accumulated mass, and faint brightness. Not out of pessimism, but out of physical accounting. Matter needs to cool, condense, fragment, and form stars. Then those stars must live, explode, enrich the gas with heavy elements, and only afterward would more efficient and visible stellar generations appear. All of this takes time. What Webb began to show was an apparent contradiction between that timeline and what arrived in the form of light. Objects too bright, too compact, too formed to be so young. It was not just a single striking image. It was a pattern that repeated across different deep fields and observation programs. In simple terms, when the telescope pointed to regions where the universe was still a cosmic teenager, it found signals that seemed to belong to an already adult universe. The first impact was the reading. Ancient light arrives stretched into infrared, and Webb detects it with a sensitivity that opens a new window. That means for the first time it was possible to build a real census of very early galaxies, not just guess at their existence. And when counting began, the surprise appeared. It was not a handful of faint spots, but a population including extremely luminous cases. Luminosity is not just decoration. In astronomy, brightness comes at a cost: energy. An object can be bright for two main reasons. Either it has many stars, which is called large stellar mass, or it has a highly efficient process releasing energy, for example, a feeding supermassive black hole. Both options are hard to accommodate too early. If the explanation were many stars, the uncomfortable question arises: how did it gather so much matter in so little time? Galaxies grow by gas accretion and by mergers with other galaxies, but in the young universe, the clock runs faster than the construction. Gravity pulls, yes, but gas also heats up, ionizes, and stirs. Furthermore, the first stars and supernovas are not a detail. They can sweep gas away, slow growth, and cut off the fuel for star formation. Even so, Webb suggested that there were systems that somehow had already accumulated an enormous number of stars or were producing light as if they had. If the explanation were a black hole, another uncomfortable question arises. Where did it come from so fast? Black holes grow by feeding on matter, but that growth has physical limits. To obtain a very massive black hole in a few 100 million years, one must start with a large seed, sustain an extremely efficient and continuous feeding, or combine multiple seeds through early mergers. Each option has costs and requires specific conditions. Then came a second surprise, more subtle and harsher: signals of advanced chemistry. The universe began almost entirely with hydrogen and helium and minimal amounts of lithium. Heavy elements are made in stars. Therefore, seeing signs of early chemical enrichment implies that previous generations of stars had already lived and died, and that the interstellar medium was already processed. The word metals in astronomy does not mean only iron. It means everything that is not hydrogen or helium. And these metals are a record of elapsed time, an internal clock. If they are present in notable levels, the universe is not only young, it is young, but it has already traveled a longer chemical path than expected. However, science is not built on headlines, but on verifications. Many of the first impossible galaxies were candidates selected by their color and photometry, that is, by how their light appeared distributed across filters. That is very powerful, but it is not the final word. The strongest confirmation comes from spectroscopy, breaking down the light and measuring lines that precisely fix the redshift. Over time, part of the confusion was nuanced. Some objects that seemed monstrously massive were not so much when models were refined, dust effects were included, emission line contributions were separated, and assumptions about stellar populations were adjusted. In other words, some galaxies were not giants. They only appeared giant because of how their light was interpreted, but the nuance did not erase the phenomenon. Even with spectroscopic confirmations and more conservative analyses, very early galaxies continued to appear that were surprisingly luminous, compact, or chemically rich. The discussion changed form. It was no longer "this breaks everything," but this forces us to refine what we thought was stable, because in cosmology, adjusting early growth is not a local detail. If the universe built large structures too early, then ingredients must be reviewed. The efficiency of star formation, the rate of gas cooling, the merger rate, the role of black holes, or even the way we interpret brightness, when the physics of the young universe does not resemble that of the current universe. Before Webb, the great symbol of this idea was the Hubble Ultra Deep Field, a minimal portion of the sky in which almost 10,000 galaxies appeared. It was not a photographic trick, it was a lesson in cosmic density, a place that seemed empty when integrated over many hours, transformed into a swarm of luminous islands. But even that lesson had limits. The early universe, stretched into infrared and hidden by dust, was not fully accessible with instruments focused on visible light. There was a background bias. We counted what we could see, and what we could not see remained off the map. Webb changes that situation in two ways at the same time. First, through sensitivity. It detects weaker signals. Second, through wavelength. It sees in infrared exactly where much of the ancient light ends up traveling due to redshift. The result is not just seeing farther. It is revealing that in many regions of the sky, the deep universe is not a set of scattered points, but a continuous texture of objects. With Webb, the black of the sky stops being black. It begins to fill with structure. The most compelling evidence of this scale leap does not come from an iconic image of a tiny field, but from something more difficult and more important, a large panorama. The Cosmos Webb program did exactly that. It did not aim at a tiny corner to squeeze it to the maximum. It built a huge mosaic to turn a section of the sky into a territory mapped in detail. And the number that comes out of that effort is the kind of figure that changes intuition. Almost 800,000 galaxies detected in an area of the sky equivalent to 3 full moons aligned approximately 0.54 square degrees. That figure is not just impressive, it is diagnostic. It means that when you expand the field of view while maintaining depth, the universe responds with an abundance that borders on saturation. In terms of density, the deep sky is much more populated than the mind expects. And from there, the phrase billions of galaxies stops being a slogan and becomes a plausible consequence of counts and corrections for objects still invisible due to brightness limits or extreme distance. In reality, the delicate point is not the exact total number, because it depends on extrapolations, completeness assumptions, and how observational biases are corrected, but the fact that any reasonable extrapolation starts from a premise that Webb reinforces. Where we once saw emptiness, there was a population. This had already happened with Hubble, when it was estimated that the observable universe contains many more galaxies than those directly counted. Considering small and faint galaxies that escaped older surveys, Webb takes that logic and pushes it toward earlier epochs and more suitable wavelengths, raising the baseline of what we know exists. But there is a second layer, even more important than the simple count. When a large and deep area is mapped, the distribution of galaxies ceases to look random. The background pattern of the universe begins to appear. Concentrations, filaments, voids, what in small photos appears as a noise of tiny dots, in panoramas becomes geography. Dense regions connected by elongated structures and relatively empty regions. That geography is key because it is not aesthetic, it is dynamic. Matter is not distributed at random. Gravity amplifies minimal irregularities, and over time, the universe organizes into a network. In Cosmos Webb, that network is interpreted not only by where more visible galaxies are, it can also be inferred by how the gravity of the total mass distorts background light, known as a gravitational lens, allowing maps of matter that does not emit light to be drawn. In fact, part of the value of the cosmos field lies in that combination. A well-studied region with multiple wavelengths, and now with the deep infrared contribution of Webb, useful both for censuses and for reconstructing large-scale structure. Webb shows that the early universe was not a desert with a few isolated spots. It was already densely active, and that forces a reformulation of the context of everything else. Because if the deep sky is saturated with galaxies, then the inevitable question is not how many are there, but what fraction of reality are we really seeing? The typical confusion arises from a calculation that seems obvious. If the universe is about 13.8 billion years old, and if nothing can travel faster than light, then one might expect that the farthest we can see is about 13.8 billion light years away. That calculation would be correct if space were a rigid stage, like a room. But space is not a room. Space is part of the phenomenon, and it expands as light travels. Three ideas need to be separated that are often mixed: the light travel time, that is, how many years it took a photon to reach us from an object, the distance at the time of emission, which tells us how far that object was when it emitted that light, and the current distance, which expresses how far today that object is after billions of years of expansion. In an expanding universe, these three quantities do not match. The photon may have traveled 13 billion years, but the current distance between us and the place where that light was emitted can be much greater, because during that journey, space was stretching. It is not that the photon broke the speed of light limit. The photon always moved locally at speed c. What changed was the size of the path beneath its feet. One way to understand this without unnecessary metaphors is to think of a simple rule. In cosmology, distance is not the length of a fixed rope, but the result of integrating how the universe's scale factor changed over time. Expansion was different in different epochs. At first, radiation dominated, then matter, and later accelerated expansion associated with what we call dark energy took over. That history of expansion determines how much space stretched while light traveled. That is why the number that seems absurd appears. The observable universe does not have a radius of 13.8 billion light-years, but about 46 billion light-years, and in diameter it exceeds 90 billion light-years. That figure is not a size of the universe in an absolute sense. It is the size of the volume from which information could have arrived from the beginning of cosmic time until today. It is a communication limit, not a physical wall. Here enters a second key concept, the horizon. In cosmology, there are horizons because the universe has a finite age and because space expands. The particle horizon defines how far information could have traveled since the Big Bang. Beyond that horizon, matter, galaxies, and structures could exist, but the light from those regions did not have enough time to reach us. They are not far away, like a distant mountain. They are beyond the causal reach of our observational history. And the Webb pushes against that horizon, but it does not break it. What it does is approach very early epochs in which light was already available to travel. However, even in that territory, there is a previous limit. The universe was not always transparent. There was a time when the plasma was so dense and hot that radiation was trapped in a soup of charged particles. Light could not travel long distances. The universe was opaque. The first free light that we can observe in traditional electromagnetic radiation comes from the time when the universe cooled enough for electrons and protons to form neutral atoms and light became decoupled, what we today see as the cosmic microwave background. The Webb does not observe the cosmic microwave background as its primary instrument, but its gaze relies on the same principle. It can only see from when the universe became transparent in certain windows. But the most unsettling part is not only in the past, it is also in the future. If expansion accelerates, there is not only a horizon backward, there is a horizon forward. There are regions of space that, even though they emit light toward us today, might not be able to communicate indefinitely in the future, because the space between us and those regions will grow at a rate that exceeds the light's ability to cut distance. In co-moving terms, in simple terms, there will be galaxies that are observable today and that, over time, will fall outside our causal reach. Not because they go dark, but because the geometry of the universe leaves them behind. This changes the sense of scale on a level that human intuition rarely considers. The observable universe is not a stable stage. It is a bubble of information whose edge is defined by expansion and by elapsed time. The Webb, by looking toward the beginnings, is building an inventory of the content of that bubble in extreme epochs. And the deeper it looks, the more evident it becomes that the cosmos is not only enormous, but that access to that enormous cosmos is governed by rules that do not negotiate with technology. They are embedded in the very fabric of space-time. Dark matter comes first because it is the scaffolding. We see it without seeing it. Its gravity organizes normal matter. In the early universe, small density irregularities grew over time. Where there was slightly more mass, gravity attracted more mass. But ordinary matter has a problem. It interacts with radiation, heats up, pressurizes, slows down. For structure to grow quickly and form filaments, clusters, and galaxies on time, a component that behaves differently is needed. One that does not emit light, does not absorb light, and still contributes mass. That is what we call dark matter. The Webb does not detect it by brightness, but by gravitational lensing. Mass curves space-time and distorts the light from galaxies behind it. That distortion is subtle when mass is distributed on large scales, a statistical stretching of shapes, a collective signal that only appears when hundreds of thousands of galaxies are measured and their orientations averaged. The key point is that when that measurement is achieved, the resulting map is not arbitrary. It shows concentrations and filaments of mass where visible light only tells part of the story. In January 2026, NASA published an image from the Webb that brings together almost 800,000 galaxies and overlaps it with a map of dark matter represented in blue. More intense areas indicate higher density of invisible mass. That data connects with the idea from Chapter 3. It is not just about counting galaxies, but using that massive count as a backdrop to measure gravitational curvature. In parallel, coverage of that same result highlighted what it means for scale. The Webb allowed observation of many more galaxies than previous maps, increasing the detail with which the invisible skeleton of cosmic structure is reconstructed. That is the first protagonist, the one that holds and organizes. The second protagonist is the one that separates. Dark energy is the name given to the observed phenomenon of accelerated expansion of the universe. It is not a poetic label, it is a conclusion based on cosmological measurements. In short, the Webb helps measure more precisely one of the universe's most sensitive numbers, the current expansion rate. That number is expressed with the Hubble constant, or h0, and for years there has been a problem that cannot be resolved with a minor adjustment, the so-called Hubble tension. There are two main families of measurements that do not agree well with each other. On one hand, local measurements based on the distance ladder tend to give a higher value. On the other hand, inferences based on the early universe, such as the cosmic microwave background within the standard cosmological model, give a lower value. If both are well measured, it means either there are undetected systematic errors, or the cosmological model that connects the early universe with the current one is incomplete. In March 2024, NASA published a result with the Webb and the Hubble that sought precisely to audit the distance ladder with an independent and more precise measurement of Cepheids. The conclusion was clear: the disagreement persists. The key phrase, turned into data is that the Webb did not eliminate the problem. It made it harder to attribute to a simple error in distance measurement with the Hubble. The important thing is to understand what that implies without exaggerating it. The Hubble tension does not automatically mean that physics is broken, but it does mean that the universe could be telling us that an ingredient is missing. Perhaps an additional type of energy in the early universe. Perhaps a modification in how dark energy behaves. Perhaps something related to neutrinos or dark matter, or perhaps a persistent systematic bias in some rung. Science is, literally, trying to close a causal loop between the beginning and the present, and the Webb, by improving precision, reduces the margin for hiding error in the details. Now it is understood why these two invisible elements define scale. Dark matter decides how fast structures grow and what shape the cosmic web takes. Dark energy decides how fast space expands and which regions, over time, fall out of reach. If expansion accelerates, the future observable universe becomes more closed in the causal sense. Fewer and fewer regions can affect us or send us information. Scale, then, is not just a size, but a dynamic boundary of communication. When looking at the early universe, the history of structure and the history of expansion become inseparable. If the Webb observes bright and mature galaxies very early, that precious growth models how gas collapses, how it cools, what role black holes play, and how much dark matter scaffolding was available from the start. At the same time, when the Webb helps confirm that the Hubble tension is still alive, it pressures expansion models, how the universe transitioned from growth dominated by radiation and matter to accelerated growth, and whether that transition occurred exactly as we describe it. In January 2026, for example, public discussion continued around the fact that the Webb is finding extremely early galaxies that are brighter, more compact and chemically enriched than expected in certain simple scenarios. At the same time, large weak lensing maps with hundreds of thousands of galaxies reinforce the reading that there exists a network of invisible mass guiding the distribution of normal matter, and there the central idea of the video is closed without needing embellishment. The James Webb did not make the universe big. The universe was already big. What the Webb did was make measurable a part of that greatness that had previously been hidden by instrumental limits. It revealed a denser abundance of galaxies in the early past, showed that the timeline of cosmic construction could have been faster or more efficient than thought in certain cases, and pushed cosmology to confront two uncomfortable facts: that visible structure rests on invisible mass, and that the universe's expansion might not be fully explained with a single closed number. At this point, scale ceases to be a number that is spoken and forgotten. It becomes a set of constraints: what we can see, what we will never be able to see, what weighed without shining, and what accelerated without appearing as an object. The Webb did not just expand the map, it sharpened the questions that the map forces us to ask, and left a final fact that is colder than any metaphor. What we know of the universe is the part that managed to send us light, and that part, even so, is already too large to fit within human intuition.